And one of the reasons this is interesting is because if something goes wrong in a space station, you don't have to send a rocket all the way there to replace it. You can just 3D print it on the spot. And I think these situations, we're slowly becoming more aware of them. And I think this pandemic is sort of almost a societal experiment in that sense, because when we had shortages of personal protective equipment, we had to go into, okay, what capacity do we have as a society to manufacture besides the big factories? People have 3D printers at home. Why can't they not print their own personal protective equipment? And so they used 3D printers in universities, in colleges, and in my university as well, contributed. And I think there are ways to take advantage of that with more awareness. And I think what this pandemic has opened our eyes to is that we need to increase our capacity of what we're able to manufacturing on the spot and on demand, because it's going to be difficult to just predict exactly what we're going to need in the next crisis. And I think just being the flexibility that 3D printing provides is going to be very attractive.
3D printing stands at the dawn of a potential industrial revolution, allowing for rapid prototyping, high customization, and removing the barriers between production and consumption.
Our guest today is Keroles Riad, a mechanical engineer and PhD candidate at Concordia University, Canada. He researches various materials for 3D printing and manufacturing, including nanomaterials and carbon composites.
He focuses on stereolithographical techniques which apply light in a 3D printing setup to shape liquid materials. He works on challenges such as making those materials be able to withstand sunlight or making them more robust.
Join us in our conversation with Kero to learn more about the cutting-edge research that he is doing, why he is concerned about the social implications of his research, and why he leads an initiative that tackles exactly those concerns.
Welcome to the second interview of the UTX podcast. I'm Ani.
And I'm Valentin. And today we talk with Keroles Riad, a PhD student from Concordia University in Canada, focusing on researching materials for 3D printing and other applications.
Kero, so nice to have you. How are you?
Thank you for having me. It's nice to see you again.
Yeah, so we've covered 3D printing, and we've actually been quite excited about how much it could change the world, and how it's one of those technologies that is really scientific and kind of futuristic, but it's still something that is within our reach. So it's really exciting to talk to someone who's kind of at the forefront of that, who is pushing those boundaries forward. So maybe just shortly to about yourself and your research, what exactly you're doing in that field.
Yeah, so I'm right now I'm a PhD candidate at Concordia University in Montreal, Canada, and I'm also a published scholar there as well. And I started getting very passionate about 3D printing back when I was an undergrad, which feels like 100 years ago, where I participated in tech engineering competition, and my participation was in the science communication category, talking about 3D printing. And at the time, it was sort of a new thing that people were getting very excited about, and we actually won first place. Back in my undergrad, I did a couple of research internships, trying to start a couple of projects with professors here, with Professor Rolf Futrich and Paula Adams here, and I just never left. So I started my master's project with both of those professors as well on making new materials for 3D printing, and my PhD followed the same trajectory.
So now your research focuses on one specific technique, or on materials and researching materials for one specific technique in 3D printing. Could you elaborate a little bit on either of those? So what are maybe we start with the materials that you're looking for, and then also how does this connect with the whole idea of 3D printing and additive manufacturing?
Yeah, so the 3D printing process that I focus on is called stereolithography 3D printing, which essentially uses liquid epoxy that solidifies with light. So epoxy is essentially glue, and what you buy in the stores usually is glue that solidifies with heat. The glues that I use uses light. So you have a 3D printing laser that traces and then the liquid would solidify in the places where the laser would pass. And then one layer at a time, you get a 3D printed shape. So there are a couple of challenges with the materials that exist for this technology. One is that it's unstable under sunlight. And that's because the same UV that in the 3D printing laser is also on sunlight, which is why you put sunscreen in the beach. And so when you 3D print a part using this process and leave it outside for a couple of weeks, the initiators that are still inside would absorb sunlight and continue to trigger polymerization reactions. And then that would make the part very brittle and it just breaks apart. So it's not useful. You cannot make anything that would last for months. The second problem is that these are plastics, so they're categorically weaker than things that you make with metals. And so this technology right now is just mostly used for modeling, just to make like a demonstration of some sort, but it's not used to make functional parts. And this is the problems that I would like to address. So in my master's research, I focused on creating new catalysts that are sensitive to light that is exclusively outside the solar spectrum. So I can have that in a 3D printing laser, but not in sunlight. So that way it's more stable. And then and that also went into my PhD as well. And then the second project that I'm working on is making those materials stronger. And the way I try to do that is by 3D printing graphene liquid crystals. Which is essentially just a fancy way of saying I want to 3D print with graphene. And graphene, as you might know, is the strongest material we know, but that strength exists only at the nanoscale. And the big challenge with it is how do you translate this strength into a macroscopic part. So this is my research in a nutshell, and it's sort of branched into quite a few different projects, just looking at each step that you need to reach that end goal of making materials for stereolithography 3D printing that would allow for the technology to be used in functional parts. One last thing I want to mention is that stereolithography is one process out of many and with 3D printing. So you can 3D print with metals already, and there's plastics, there's chocolates, there's biomaterials, you can 3D print with moon dust. Which is quite interesting because then you can send a rocket with a 3D printer and just use the material you find on the moon to build the colony, right?
Amazing.
So my goal is to make stereolithography on potential technologies that you use to make functional parts, because there are other technologies that exist that you can do that, but they also have a lot of drawbacks that stereolithography does not have.
So why did you choose stereolithography as your main research area? Why do you want to work with liquids? Where do you see the advantages of focusing on that?
So right now the replacement, the way 3D printing is replacing conventional manufacturing is through metal 3D printing. And there are a couple of problems with that. One is that it's very energy intensive. So let's say you 3D print with titania, you have like a bed of powder, of titania powder, and you have to heat that right below the melting temperature of titania. So it's not molten yet, but it's just close enough. And then you have a laser that locally heats those titania powder to center into a solid, right? And so this is very energy intensive, and I'm somebody who also really cares a lot about the climate crisis, and I think it's really important that the technologies we develop are take that into account and how much energy they consume. So that's one issue. The other part is that the parts that you make with metal 3D printing don't have the same kind of qualities that you get with stereolithography because the surface roughness is very bad. And there are ways to mitigate that, but it's always added processes that at some point it becomes, it takes away the advantage of 3D printing because it becomes more complicated to get to a reasonable part. And so one of the research, at the beginning of my project, I went to a 3D printing company called Access Prototype here in Montreal. And they mentioned that they have a lot of clients or a lot of projects trying to make 3D printed parts for the cockpit in an airplane. But the quality of the 3D printed metal 3D printed part is not very good. That if they have the choice to switch to stereolithography because the surface finish is much better, then they would do that. But the reason they cannot is because it's very unstable. You will not get to an airplane with parts that are made with stereolithography right now because it's, you know, a couple of weeks it will break apart. It's not safe. And so if you are able to just address the stability problem, even if the parts are still plastics that are categorically weak, they will already have many more applications replacing metal 3D printing. Because if it's not a high stress application, but you have a better quality part, then you're able to replace it.
And could graphene be the potential solution to the problems you mentioned?
So I think graphene could help with the strengths issue, not the stability, not necessarily the stability problem. So these are two distinct problems, and I think eventually somehow those research has to be combined so that you have a stable and strong part. Graphene would help make the part stronger. So my goal with that, so right now there are a lot of research making graphene paper, for example, where you have the graphene sheets orient to parallel to one another. So you have like parallel sheet, and these paper have already strengths higher than some of the metals like aluminum and so on. And the reason that works in research is because they have heat curing. So they have the epoxide groups on graphene oxide reacting with one another so that those sheets are actually bonded to one another. And so the strengths of the graphene sheets, which are the strongest material we know, but that strength also exists only in nanoscale, is translated into bigger parts. It doesn't capture the entire strength of the graphene, obviously, because the graphene oxide weakens the part, and also you're still bonding things together. It's like having a brick that's very strong, but you still have to bond them with cement, right? The wall is not necessarily as strong as the brick. But my goal is to be able to do this process with light, because then if I can do that with light, then I can 3D print graphene oxide. Right now, what's possible with the research is with heat. And as I said, I just want to do that with light, because then you can 3D print using stereolithography with graphene. And if I'm able to get strengths or mechanical properties that's comparable to what's already being achieved in literature with heat curing, then that's already a big step. It's a big improvement over what currently exists in terms of stereolithography. And you know, there are different ways of doing this. It doesn't have to, like the photocured part with graphene doesn't have to already achieve these high properties right away. You can 3D print with light to get the shape, and then you can do post-processing with heat so that it's stronger. So this is right now my second project that I'm working on.
Could you also extend on the other side when we look at what potential sources of the spectrum we could use when you're saying light? What could be suitable for conducting stereolithography in that sense? What could be something?
So right now the ozone layer blocks everything below 300 nanometer, which is why we don't all get cancer. So right now, if you're able to have the Foot-Curing reaction triggered by light that's below 300 nanometer, exclusively below 300 nanometer, so you could have an initiator that has absorption below, like the peak absorption is below 300 nanometer, but it still have some sensitivity to light above 300 nanometer. So if you have a catalyst that is responsive only to light below 300 nanometers, then in theory at least, or in principle, you're able to 3D print because you can make lasers that have light below 300 nanometer. But when you leave it outside, the ozone layer sort of protects you. It's like the big coating that exists around the planet. Because right now, the way it's being mitigated is that they have coatings on top of parts to make them last longer, but it doesn't prevent the problem. It's like putting sunscreen again. You're literally putting sunscreen on top of the part. It goes away. And it slows down. So the part, instead of breaking up in like a week or two, it breaks up in a month or two. It's still a problem. My goal is to eliminate the whole root cause of it.
Wow. So this is, I guess, if this happens to become true, I guess there's a lot of applications for it in the future. And when we look at the different industries that 3D printing or new manufacturing techniques, that additive manufacturing techniques are being applied to, we ourselves, we think about manufacturing and also like a bit more out there stuff like food. For you, why is it really exciting to you to focus on these things? Why does it make your heart smile when you can solve these problems?
So now as an engineer, when you design a part with conventional machining, you're always worried about the limitation because of manufacturing. It's not design limitation. It's really just where the cutting edge is going to come from, so that you're able to make a part that you're trying to design. So if you're trying to drill a hole in the wall, you need to access a wall. The drill needs to be close to the wall so that you can drill the hole. But with 3D printing, you can make very, very complicated shapes, some of which are impossible to machine, right? Just simply impossible. But beyond that, it's also, you can have very complicated shapes that would have been very, very expensive with conventional machining, but would be just completely possible and reasonable to do with 3D printing, because you're adding layers. So it doesn't really matter how complicated the design is. Right. And as an engineer, I feel like this is everybody's dream in terms of engineering, that I just want to imagine something and I want to be able to make it. I don't want to be sort of chained or restrained by the manufacturing limitation. And I think this is sort of the promise of 3D printing. But right now, the bigger problem is that even if I can make whatever I can dream of in terms of design, I cannot use it, because right now the material doesn't exist where you're able to make something that's usable. So think about, again, my background is in aerospace, so I think about airplanes quite a bit. But let's say you make very energy efficient design, or aerodynamically efficient design, whatever, that would consume less fuel and be lighter and all these things. And the only reason you cannot make it is because the material is weak. So you can 3D print it. You probably cannot manufacture it conventionally because it's too complicated. But if I can 3D print it, I can see it, I can test it in a wind tunnel, but it would break apart in 2 weeks. This is a big problem. So if I'm able to eliminate this, or at least mitigate this problem, I'll feel much better.
Yeah, so you mentioned that like specifically aeroplanes. So what specific parts? Like, so we discussed that there might be some applications for, or like in some cases actually 3D printing is already being used in rockets and aircrafts. But like in the grander context of rockets, aerospace, and then space, what do you think 3D printing will be able to do?
So I think what we in terms of parts, we're talking about lower stress parts of in the airplane. So we're not talking about things like in the engine where there's a high heat and high pressure. I think this is sort of the beginning, sort of you're testing with uncritical parts that don't have to withstand a lot of stress. And one of the challenges of 3D printing is because almost every part is slightly different. So there's going to be a lot of work and repeatability and testing to make sure that every part you're making actually meets all the requirements. So I mean, for example, think of if you have an alloy or a titanium block, right? You make your standard sample and test it. But with 3D printing, you're making very, very complicated shapes. It's actually very hard to measure exactly what the properties are of that. And so there's a lot of, there's going to need to be a lot of work around that. How do you standardize testing for 3D printed parts? And how do you regulate the whole thing and make sure that it's repeatable? Yeah.
Can you extend again on the different properties that 3D printed materials might have? For instance, in an airplane, it might be lighter, you can save some weight. What are like the exciting properties that you see where really, apart from the idea of rapid prototyping and making things faster and being able to, as you said, do all the things that you imagine to do, what are really the main properties where you see, okay, it has big advantages in comparison to traditional materials?
I think when we talk about making things lighter, right? So, okay, with stereolithography, because you're not using metal, it's naturally going to be lighter. But in terms of making things lighter by design, so think of a hollow sphere, right? it's lighter than if you have a full sphere, right? Because the core is gone. And this is sort of the kind of things that you're almost able to make with 3D printing, where you can sort of hollow out certain parts as long as you have the right properties. That way, by design, you're making what you 3D print lighter. And I think this is exciting for me as somebody who wants to fight the climate crisis and lower our energy dependence and efficiency. Because then if you can make parts lighter, then you don't need as much fuel to fly them, right? And that also makes it a bit even more possible when we talk about electrifying like airplanes. So you don't have to burn fuel, you can use electricity and you can use batteries. If you can lower how much energy you need, you're a bit closer. And just, yeah, so I think it just in terms of efficiency, I think this is what excites me. But there are quite a few different properties that I think excite different people as well. But at the end of the day, it really depends on the materials that you're going to end up developing, because right now existing material, you're very limited by them. So it's hard to speak about material properties now because I don't know what exactly are the materials that's going to actually meet or is going to allow 3D printing to be used in functional applications beyond what's being used right now.
So that leads us to a next question, which is, what are the main challenges to 3D printing adoption? And it seems that from what you're saying, yeah, obviously as you're researching on it, there is still a lot to do in terms of developing the technology further. So is this the main reason, or do you also think there's other societal reasons, let's say, or lack of funding even, that 3D printing has not sort of received the mainstream attention and the adoption cycle that it sort of deserves?
It's complicated. So technologically, I think, at least from an industry point of view, I think material is the biggest obstacle. Societally, like if you talk about having 3D printers replace normal printers at home, I think this is we have to be very, very careful with that, because I don't want people to 3D print a new pair of glasses every day, because that would create so much waste. And I think we have to be very, very careful about the social impacts of the technology we're having and we're developing. And so it has to be very, there has to be a conversation and sort of societal discourse of how to use technology without creating a whole list of new problems. And so that's what tends to be my concern, because as I mentioned, I care a lot about the climate crisis and the waste crisis, and at the same time I'm working on this technology that has a lot of potential advantages when it comes to fighting these issues, but there's also risk when it comes to people just creating everything that comes to their mind, even if it's not necessarily wise to do that. Having said that, I don't think that, like, I haven't met a lot of people who don't know what 3D printing is right now. And so I think there's a lot of awareness. And I think back when I first started to learn about this technology, it was new and there's a lot of hype about it. And I think at some point we sort of started getting this realization where we're taking a step back and realizing the limitation of the existing level of technology. And I think what's needed is research. Trying to develop the materials that allows industry to take advantage of it. So that we're more efficient. And the other example I would mention is that at the beginning of the pandemic, there was a tweet by our Prime Minister, Justin Trudeau, who essentially called on everybody who has a 3D printer to 3D print personal protective equipment, like face shields and so on. And I think this is almost like a very good demonstration of what's possible with 3D printing when you're sort of taking ownership of manufacturing, because then you're no longer dependent on things being shipped from across the ocean, where you have the ability to build critical supplies on demand and on the spot without having to do all the transportation and shipment and storage. And I think this is something that we haven't taken good advantage of, and I think we slowly are. So, I mean, for example, there's 3D printers on the International Space Station. And one of the reasons this is interesting is because if something goes wrong on the space station, you don't have to send a rocket all the way there to replace it. You can just 3D print it on the spot. And I think these situations, we're slowly becoming more aware of them. And I think this pandemic is sort of almost a societal experiment in that sense, because when we had shortages of personal protective equipment, we had to go into, okay, what capacity do we have as a society to manufacture besides the big factories? People have 3D printers at home. Why can't they not print their own personal protective equipment? And so they used 3D printers in universities, in colleges, and in my university as well, contributed. And I think there are ways to take advantage of that with more awareness. And I think what this pandemic has opened our eyes to is that we need to increase our capacity of what we're able to manufacturing on the spot and on demand, because it's going to be difficult to just predict exactly what we're going to need in the next crisis. And I think just being the flexibility that 3D printing provides is going to be very attractive. Once again, we have to do this very carefully because we should not have people 3D printing a new pair of glasses every day.
Do you think that in the future, when, let's say, it will be available to people, that everyone can sort of 3D print their own stuff at home, and the whole idea of we're producing too much waste and consuming too much carbon dioxide intensifies, is there any other way out than, let's say, have purely biodegradable materials that are fully recyclable, sort of a circular economy approach? Or should we also just rethink our connection to stuff, just produce and consume less stuff? Do you think technology is, or what will happen faster? Will we become more conscious faster, so to speak, or will technology help us getting there? What is the way out, so to speak?
So I don't know what will happen. I know what should happen. So, okay, so there's a couple points here. One is that there's absolutely no alternative to reducing our waste and reducing how much stuff do we need. So when we talk about biodegradable and compostable plastic, a couple months ago, I visited a composting facility with my team because I run another project called Waste Not Why Not, which tries to help the community learn how to compost and reduce their waste. And the composting pile was so full of plastic, and a lot of it, they said, is things that are marked as biodegradable and compostable. So even though something is marked as biodegradable, compostable, doesn't mean it's actually compostable. And so there's a lot of greenwashing out there that exists. It's not necessarily to say that it's impossible to compost things like PLA, which is made out of corn starch. But it takes much more complicated technology that simply doesn't really exist right now, or it's not widespread, and it's not used widely yet. And it not only is it not composted, it also contaminates the recycling stream, because this plastic is not, it looks similar to other kinds of plastic, so it contaminates that. And so actually it's the right place to put compostable plastic as a garbage in most places. And so it's hard to just use that as an excuse. Having said that, there are also other projects here at Concordia called CP3, which is trying to collect 3D printed part. And so we're talking about things that are made with plastic filament like ABS and PLA, and just try to use that into creating more recycling that into new plastic filament for 3D printing. So use a 3D printed part, and then you go through the machine to make turn it back into filament. And that's an okay approach, but at some point, everything that we generate actually goes to landfill eventually, because the quality of everything decreases. And so I think what needs to happen is there has to be a lot of awareness in making sure that people understand that recycling, compostable plastic, all of these things are tools, but they are not solutions. And at the end of the day, they have to reduce our waste, and the reality is that not everything we buy we need, and I think we have to be a bit more aware of that.
So you also lead the Waste Not Want Not campaign. Do you see any possible marriage between kind of composting and recycling and 3D printing? And if so, are you like considering any kind of research strands in that direction?
So the Waste Not has absolutely nothing to do with my research. It started as a side project that just grew very fast, very quickly, and I just love it so much that I always continued. How do you connect that with 3D printing? I think because 3D printing is going to replace a lot of manufacturing in the future, there'll be a lot of things that are going to be made by 3D printing. And even though, you guys are talking about how slow it has been to adopt 3D printing, it is the future. At some point, no matter how slow it is, we're going to get to a point where a lot of what we do, a lot of what we make is going to be made by 3D printing. And I think that conversation around waste has to happen when it comes to about what's being made by 3D printing. Yeah, so projects like CB3 that I mentioned at Concordia that tries to sort of mitigate that is helpful. And I also think there has to be a lot of work on education around 3D printing waste as well.
When you can imagine the future sort of 3D or even 4D printing and the materials that we will be able to use for these manufacturing processes, do you have some sort of dream where for what's going to happen, for what we will be able to do, that we can have like I don't know, material, just an example of materials that inherit a computer chip and then some sort of smart dust or something like that, where you have some inherent connectivity added to the material, where, I mean, it's not that out there, but I mean, how in the future, where you see like what will be widely adopted? Let's say we go 20 years into the future. Have you ever thought about yourself, okay, where can I take this myself as well in that future?
So I think with more research in terms of material, I think industry is going to use 3D printing more and more and create things that are simply not possible right now. Because so right now when we're talking about adding conductivity and all these things, these are because you're able to 3D print with multiple material and almost 3D print assemblies with movable parts without having to fasten anything, or like you can do this all at one shot. I think this more integrated approach is going to be used more and more in the future to do things that are simply not possible right now. So I think there's a lot of room for industry to take advantage of 3D printing, and stereolithography is not technology that you can 3D print at home with. It costs like I don't know. I remember when I started, it was around $250,000 to have a 3D printer. So it's not something that's like an everyday kind of use for home. It's more like an industrial process. So I think for industry, I think there's a lot of rooms there. For individuals, there's also a lot of rooms where we're talking about children and people making designs, and they just see what they're making and sort of making changes this way and sort of taking ownership of the things that they use and how they're designed and how they are made. But again, there's also social risks that we have to be aware of. So I think 3D printing is something that excites me a lot and also scares me a lot. And I think that's true with almost every technology that we develop. There's a social impact, positive and negative, and I think that all of it has to be part of the conversation.
The pattern that we oftentimes see is that exactly those people that know most about the technology, just like in your case about 3D printing, are also almost scared about it the most. And when we talk about the famous person, Elon Musk, saying that manufacturing is the bottleneck for human progress, and we put a controversial question whether engineering is what drives progress forward most, or whether it is let's say the software side, the intelligence to it. Where would you stand on that point? Would you, if there was like a spectrum, where do you say is like the core of innovation of humanity happening?
Oh boy. So at the beginning, I think before, I mean, internet and computers are not that old, right? And I think before that, the more we're able to improve manufacturing, that was driving our progress until the computer and internet started to take off, and that sort of switch how we're moving forward. And I think it's going to be like a how do you say sort of going back and forth between the two, and sort of like a pendulum of some sort. I don't think there's only one of them. I think at some point also they're gonna almost merge, because when we're talking about 3D printing, we're talking about things that we can program and almost replace manual labor, which also has another social risk behind it. But we're talking about computers improving the designs on their own and just programming the whole thing in terms of improving software as well for 3D printing to allow us to improve the parts that we're making with 3D printing. Yeah, so I think it's a little pendulum that at some point it's just going to merge, and it's going to be difficult in the future to differentiate between the two.
I mean, we've already asked you sort of about the future and sort of your prediction of what's going to happen, and we're aware that it's quite hard to do. But It's just interesting because when you get a person like you talking about these things in our podcast, it's always interesting to us to sort of have an idea of what you think how the future will look like. And maybe on this side, if you could sort of create a utopia, like, first of all, what do you think? How long will it take? Because you're convinced that 3D printing will definitely become a mainstream subject, and that vast amounts of of the stuff that we produce will be produced by 3D printer. When do you think this is going to happen? And then secondly, and especially also regarding reducing waste and still increasing our living standard, which not necessarily is conflicting targets, where do you see a balance in the future that is ideal? How could that future world look like to you?
So I don't know when. I think it's going to be very difficult to do that, mostly because if you look at the beginning of the pandemic, if you ask anybody how long it would take to make new vaccines, you'll say 5 years max. But we have made not only one vaccine, but 4, at least so far in Canada, that have been approved in 1 year, in less than 1 year, right? So I think it's, no matter what prediction I could try to make in terms of timeline, it's going to be wrong. But I think it's only going to get faster in terms of our transition into from conventional machining to 3D printing. And this is as a part of it too is nanotechnology, and how nanotechnology also impacts 3D printing and the materials for 3D printing. So one of the projects I work on is, when I talk about stability, I try to use nanoparticles to as a catalyst that I can control what light they respond to. And so this is how I met Ani. Is I went to ETH to work with Professor Batsinis in a particle technology laboratory for a couple of research internships, and I got to learn about how to make new nanoparticles in there, and using the flame sphere pyrolysis, which is essentially you have chemicals that include the metal elements, you make them with flammable solvents, and you literally put the whole thing on fire. It's actually quite satisfying if you're upset. And so I was able to make the right nanoparticles, and technologies like this, they're very versatile, that you're able to manipulate and change the composition of the nanoparticle, change the properties, change the size, and like this, it's just very quickly. And I think that will also sort of accelerate how we're developing new materials and how we're developing new technologies. And I think it's really only starting now. I think, well, nanotechnology exists for a while, but I think it's only now that's sort of picking up a lot more speed on how it translates into commercial applications right away. Actually, Concordia has the first FSP in Canada now that my professor has bought. Just after I came back, and in a couple of weeks we'll also have a big event where Professor Martinez from ETH and Professor Alexandra Taliki from Sweden and Professor Reza Holgi from Carleton is going to speak about that technology. So I'm actually inviting your viewers to participate.
That would be great. Yeah.
Information.
Yeah, definitely also to the audience if you're interested in that, and that sounds really exciting. Something more towards, because you mentioned also nanoparticles, towards sort of your other research stream, to pick up that one again. Could you elaborate a little bit more on the use of quantum dots, and what are the sort of the current challenges that you're facing with bringing those in?
Yeah. So quantum dots are very, very small kind of nanoparticles. So nanoparticles are already very small. Like 1 nanometer is 40,000 times smaller than one human hair, right? And the quantum dots are on the end, are on the extreme end of that. So we're talking about things that are smaller than 10 nanometer in size. And the superpower of quantum dots is that you can control their band gap energy, or in other words, the kind of light that they respond to, just by controlling their size. And this is why working with the flame sphere pyrolysis was very interesting, because it can control the size very easily. And as I mentioned earlier, I want catalysts that are able to respond to light that does not exist in the solar spectrum. And so I was able to prove in my master's that I can use semiconductor nanoparticles to photocure epoxy, which is the reaction that's used in stereolithography 3D printing. But I didn't have the right nanoparticles that has the right band gap energy that would be insensitive to sunlight. So I was able to prove it with titania, but that doesn't solve my problem because titanium is also sensitive to sunlight. And so by being able to make quantum dots that have the band gap energy that's bigger than what's available in sunlight, then I'm able to use my research in terms of using those semiconductor nanoparticles for the Kero epoxy, but use that with quantum dots. And then in principle, that would be a more stable part, because then I can excite the quantum dots with my special light, and then you can put that in sunlight and would not be affected. So this is how I'm using it. And with FSP, I was able to make the right quantum dots, and actually my paper is hopefully coming out soon. It's very close, and essentially the challenge with quantum dots are a couple of things. One is that they also are unstable in their own right. So if you have like zinc oxide quantum dots, it will grow over time. And if you have used light or chemical reactions, it will also corrode. And so you have to make sure that you're able to make quantum dots that are stable. And the way I'm trying to make that is by embedding them in amorphous matrices. So just putting on in silica, because then that silica sort of acts as stabilizers. But you have also to be careful when you do that, because you don't want to completely close off the surface, because then you don't have any reaction. So you cannot put it in glass and then hope that it's going to do anything. So it's a balancing act, and so far it seems to be going okay.
Awesome. Yeah, what a great outlook on what the future will look like of how we do our stuff and with which materials. Any question? Any other question from your side?
Not really. I think, yeah, it's really fascinating, especially tackling the two main problem aspects that you mentioned, stability of materials and its kind of susceptibility to light. And yeah, we definitely wondered, because yeah, like SLG was invented back in the 80s. I mean, it's almost 40 years now. And it's such a revolutionary technology that we're kind of surprised that it hasn't taken the world by storm, where you could, as you mentioned, literally break the chains free and produce anything you want. So, I mean, we look forward to your work, hopefully changing that and making it more accessible, and at least in the public's eye, to make it a real, an everyday tool. But I think, as you mentioned, yeah, there are still challenges involved, even if we solve these problems. Waste recycling, our relationship to consumption and items. So there are definitely still some things there, but yeah, it's nonetheless a very bright outlook.
Appreciate it.
Yeah, thanks so much, Kero, for being part of the podcast, and all the best for your PhD research.
Thank you for having me, and I really appreciate the discussion.
Yeah, thanks for your time. It was great to not just get to know kind of your work, but also to see that it's really driving the world forward to a place where we have more 3D and 4D printing.
And hopefully, still less waste and less. Yeah, let's say, but as you said, I think it also is on us to sort of change our mind on our relationship with stuff. Otherwise, it's not going to work. Yeah.
It's a fundamentally social problem. You cannot have a technological fix for it. At the end of the day, we're the one buying, we're the one driving consumption. And so you can talk about technology from here to the moon. At the end of the day, it's a social problem.
Yeah.
So technology has a role to play, but it's not the solution.
Absolutely. Yeah, well, I think thanks a lot for taking your time.
All right. Well, thank you very much for having me and for reaching out. And it's nice to catch up with you.
Yeah,
nice
for sure.
All right. Well, enjoy. Have a good day.
You too.
Have a good day, Kero. Thank you very much.